This is your first official calculus lesson. It is on the definition of the limits and a graphical approach. You may be familiar with the phrase reach your limits. Generally, it's used when somebody's trying to reach for the best possible result. You will also implicitly use it when you slow down your car after seeing a speed sign. Now, suppose you want to graph this rational function, f of x equals x cubed minus 1 over x minus 1. Here is the graph over to the right. For all values of x except x equals 1, you can use standard curve sketching techniques. The reason it has no value at x equals 1 is because the curve is not defined there. There is a hole in the graph. So in order to get an idea of the behavior of the curve, we're going to complete the chart below. So at 0.75, it's approximately 2.3125. At 0.95, it is 2.85. At 0.99, it is 2.9701. At 0.999, it's 2.997. Now we have that point discontinuity at 1, so at 1 it does not exist DNE. At 1.001, it turns out to be 3.003. At 1.01, it's 3.0301. At 1.1, it's 3.31. At 1.25, it's 3.81. So what we see in this chart is that in the neighborhood of 1, so looking to the left and the right of 1, this would be to the left of 1, highlighted in yellow. And this would be to the right of 1, highlighted in green there. So in the neighborhood of 1, it's approaching 3. So our limit is actually going to be 3. So the limit doesn't ever get to 3 in this function. It does not. Okay, so that will bring us to our informal definition of a limit. It's what's happening to y as x gets close to a certain number. The function doesn't have to have an actual value at that particular x for the limit to exist. Limits describe what happens to a function as x approaches the value. In other words, a limit is the number of the value of the function should be equal to and therefore is trying to reach. Here's our formal definition of the limit. We could say that the limit of f of x as L, so L is just a value, approaches C, provided we can make f of x as close to L as we want, but it's not actually letting x be C. So that just sounds a little bit confusing. This is how it's written, and you would read it as the limit as x approaches C of f of x equals L. Okay, so now we have a two-sided limit. In our previous example, as we approach 1 from the left, it means that value of x is slightly smaller than 1. So remember the left was, I think I highlighted in yellow, I'll match the colors. Left was over here. Right was over here. So here's the left, and here's the right. It's going to become closer to 3. The idea of approaching a certain number on the x-axis from different sides leads us to the general idea of a two-sided limit. So we have left and right-hand limits. If we want the limit of f of x as we approach the value of c, from the left-hand side, we were going to write limit as x approaches c, and then you're going to see this little minus sign right there. That doesn't mean it's a negative c, that means it's coming from the left. So you see a little minus sign after, it's coming to the left of f of x. If we want the limit of f of x as we approach the value of c from the right-hand side, you'll have that little plus sign right there. Plus means the right-hand side. So overall, in order for a limit to exist that it approaches some value c, it must approach the same y value from both the left and the right. And this is how we'd write it out. Limit as x approaches c from the left of f of x equals limit as x approaches c from the right of f of x, which equals your limit as x approaches c, which is going to equal L, just some value. If this does not happen, we're going to say that the limit does not exist, and we can abbreviate that DNE. All right, so here's our formal definition of writing it out. If your limit doesn't exist, this is how we want you to write it out. Limit as x approaches c of f of x does not equal the limit as x approaches c from the right of f of x. Therefore, your limit doesn't exist. All right, so let's look at all of these on a graph. First, while looking at the graph, I'm noticing right here, point discontinuity. Right here, jump discontinuity. And then another point discontinuity right there. Okay, so our limit as x approaches -2 from the left. Okay, so -2 from the left, we're looking over here. It is approaching -1. -2 from the right would be coming in right over there on the right-hand side. It's also approaching -1. So since your limit coming from the left and the right equal the same thing, we can say that limit of as x approaches -2 exists. That's equal to -1. Now our function value is not -1 though. Our function value is up here. F of -2 is 5, which is fine. As long as you're coming in from the left and right-hand side to equal the same value. We're not actually getting to that value of -1, we're just approaching it. Okay, now let's look at the value 0. This one seems a little bit easier, which is nice. Okay, 0 coming in from the left is 0. 0 coming in from the right looks like 0. The limit, so limit from the left and right equal each other, so that equals 0. So our function value equals 0. So this is nice. That's a continuous function at 0 right there. You could write that out. This is just a little preview for what's to come. This is continuous at x equals 0. That says 0 because your limit as x approaches 0 from the left of f of x equals the limit as x approaches 0 from the right of f of x, which equals our function value at 0, f of 0. So that's nice. Whereas at -1, the example before, we weren't continuous there. All right, let's look at the next example. I'll switch colors. We'll go green. Okay, limit as x approaches -2 from the left. Right there, we're approaching 1, the y value of 1. Negative, as x approaches 2 from the right, not -2, +2, we're approaching 2. So here's where our limit does not exist, because these values coming in from the left and the right are different. The function value does exist. We're looking at that closed circle right there, so f of 2 equals 2. All right, so we could write that out if you were asked to. You could say the limit as x approaches 2 from the left of f of x, and this notation's important, does not equal the limit as x approaches 2 from the right of f of x. Therefore, 3 dots, therefore, the limit as x Scroll up a little bit. As x approaches 2 of f of x does not exist. All right, last example on this page, we have our limit as x approaches 5 from the left. Okay, 5 from the left. Looks like we're going towards 2. 5 from the right, also going towards 2. Limit as x approaches 5 is also 2. But f of 5, we don't even have a function value. There's an open circle there. There's no dot anywhere, so we're just going to write dne for that. Okay, let's look at our next example. Okay, our limit as x approaches 2 from the left, so we're coming in this way. Looks like that is 4. Our limit as x approaches 2 from the right equals 2. So our limit as x approaches 2 does not exist because it's different coming from the left and the right. Our function value at 2, we have our closed circle right there at 4. Okay, example 3, what I want to do is, I want to get rid of this dot here. I didn't mean for that to be there. Okay, so get rid of the dot. All right, now our limit as x approaches -1 from the left. So we're looking right here. It's going to keep going up. We have that vertical asymptote right there, or infinite discontinuity. So as we're coming to -1 from the left, it looks like it's approaching infinity. It's going up. -1 from the right is going down. So that's going to be approaching negative infinity. Technically, infinity and negative infinity is also, it does not exist, but you can be more specific with infinity and negative infinity. The limit as x approaches -1 does not exist because it's going up towards infinity to the left and down towards negative infinity to the right. F of -1, since I erased that dot, I didn't want that point to be there, we're going to say does not exist. We got an infinite discontinuity right there. Our limit as x approaches negative infinity. Okay, so as we're going to negative infinity, as we're going this way, our function is leveling it out. It looks like it's getting closer and closer to 0. And as we're going to positive infinity, same thing's happening over here on that right-hand side. It looks like it's getting closer and closer to 0. Okay, example 4. So this function is kind of weird. This is what is called an oscillating function. So it's like coming in and then it's going crazy. You can't see it that well, but it's like going up and down super fast, approaching the origin. So this is called oscillating. Let's see if I could spell that right. 5th grade spelling champion right here. All right, oscillating. So as it approaches 0, it keeps going up and down. It's not approaching an actual y value because it's going up and down super fast. So we're going to write does not exist for that. Okay, now we kind of have a little composition of functions with these graphical limits. So what we're going to do is work same way as we would do this working inside out. So you would do this inner part first. So we're going to start out saying, okay, the limit as x approaches -3 of f of x. Okay, f of x is in purple. So as we're approaching -3, looks like we're going to -1. So that equals -1. Okay, and now the next part, we're going to use this -1 in the next part. You're going to write your limit as x approaches -1 of our outer function, g of x. So this changes, that's where x is approaching now, of g of x, and as x approaches -1, from the left and right, it's approaching 1. Now the function value is 2, but that doesn't matter because we're asked for the limit, so here's our final answer, 1. Okay, so same type of thing in the next problem. Now limit as x approaches 1 of f of g of x. Okay, so we're going to start with our inner function here, g of x. That's what I'll write first. We'll change colors. Limit as x approaches 1 of g of x. Okay, and as x approaches 1 of g of x, here we are from the left and right, and the function value all equal -1. Now we're going to write our limit as x approaches -1 of our outer function, which is f of x. So remember, this came in over here. And as we approach -1, we're having a little bit of an issue because from the left and right, it's approaching different values. So this is going to be a DNE, does not exist. Okay, a couple more graphicals, let's look. We got a nice sine function, starts at the origin, just plain old f of x equals sine x. Our limit as x approaches 0, so coming in from the left and the right, looks like it equals 0. Here's 2 pi, so that's going to be pi right here. This will be pi over 2 for our next example. All right, limit as we're approaching pi over 2, we're getting close to 1. We are going to actually get to 1 for that one. All right, as we approach -infinity, as we're going this way on the graph to the left, we keep going up and down between -1 and 1. We're not getting to an actual value, so that's going to be a DNE, does not exist. Same thing if we're going to the right, towards positive infinity. All right, whereas example 6 is a little bit different because your limit as x approaches 0, all right, that's just going to be 1. As we're approaching -infinity, yes, it is going up and down, but it's flattening out and it's approaching 0. So that, as we go to -infinity, is going to be approaching 0. Same thing if we go to a positive infinity, it's approaching 0. All right, few piecewise functions over here. If we need to do the limit as x approaches 1 from the left, we need the part of this which is going to be less than 1. So we're looking at that part right here. So what we're going to do is just sub in 1 for x, so that's going to be 3 minus 1, and that'll be 2. All right, limit as x approaches 1 from the right. We're going to be looking at that part right there, a little bit greater than 1. Again, just sub in that 1 into the function, so it's going to be 1 squared plus 1, which is 2. All right, that's great because now we know our limit exists because our limit coming from the left and the right equal each other. So limit as x approaches 1 is 1, not 1, 2. And then f of 1, our function value at 1 is not the same. Our function value at 1 is 4. So that tells us that our limit exists, but this is not a continuous function, since our function value is different from the limit. So we can tell that on a piecewise function that way, rather than, seeing it on a graph. Okay, example 2, limit as x approaches 2 from the left, so we want a little bit less than 2, and that's going to be 3, it's just the value 3. 2 from the right, a little bit greater than 2, so it's going to be 6 minus 2, which is 4. Our limit as x approaches 2 in this one does not exist because our limit from our left and our right are not equaling each other. All right, and the last part, f of 2, we're going to use this function right here because it has that equal to sign right underneath it. So f of 2, our function value at 2 is 3. A good way to write this out, again, is our limit as x approaches 2 from the left of f of x does not equal our limit as x approaches 2 from the right of f of x. That would be your reason why. All All right, computing limits without your calculator. What we're gonna do here is it's kind of the same thing we were just doing in those piecewise examples. It's called direct sub. So you're just gonna sub in the value for x and see what happens. Okay, so your limit as x approaches pi over 2 of 3 sine x is going to be 3 sine pi over 2. Okay, so pi over 2 would be right here. That's the point 0, comma 1. Remember, your points are always cosine, comma sine. So your value is going to be 1 right there. It's 3 times 1, which equals 3. Okay, number 2, we're going to substitute in. It'll be negative 3 times 3 squared plus 7 times 3. So if you're not using your calculator, steps you'd probably take would be negative 3 times 9 plus 21. And then you'd say, all right, that's negative 27 plus 21, which is negative 6. All right, we got an e and a natural log here. Now it's getting fun. Limit as x approaches e of natural log absolute value of x. So I'm going to put a star next to that one, because anytime you have like logs and e's, you got to remember some rules. All right, natural log absolute value of e. Well, the absolute value of e is just going to be e. And natural log of e is 1. We know that from prior chapters. All right, number 4. Limit as x approaches 3 of the absolute value x to the 4th minus 2x cubed minus 30. So just sub in 3 to the 4th minus 2 times 3 cubed minus 30. You end up doing that out and you get negative 3. I'll just tell you that to save some time, which is 3. Absolute value of negative 3 is 3. All right, up to 5. Okay, so 5 is interesting because it doesn't say the limit as x approaches 4. It wants 4 from the left. So if we look at this, I'll use a different color for fun. Another color, blue. If we look at this, if we just sub in 4 to this, 4 squared minus 16, I need that absolute value, or not the absolute value, the square root. That's going to be square root of 16 minus 16, 0. That equals 0. But they said 4 from the left. And the tricky thing is you got to remember with radicals that if you have a negative underneath a square root, you're going to have an imaginary number. So if you sub in a value less than 4, it turns out to be imaginary. So for example, if we put in like x equals 3.9, we do square root 3.9 squared minus 16, that ends up being the square root of negative 0.79, which is an imaginary number because we have that negative underneath. So the answer to this, instead of being 0, is actually does not exist. So that was tricky. Star that one too. Okay, 6 is just another direct sub, so we're just gonna plug in negative 2, negative 3 times negative 2 cubed plus 4 times negative 2 squared minus 10. That's going to end up just being 30 when you solve that. Number 7, plug in negative 5. Doesn't matter on this one if you're coming from the left and the right. What happens? I'll answer my own question. You get negative 1, which is imaginary. If you get an imaginary number, that's going to be DNE, does not exist. All right, and last one. Limit as x approaches 0, natural log 2x. So if we sub that in. That's going to be natural log of the absolute value of 0. 2 times 0, which is 0. That does not exist. Remember your natural log graphs looked like that. If we're doing absolute value, it's going to look like this. So it actually does not exist there. You could technically be a little bit more specific and say negative infinity, because it is, as it approaches 0 over here. It's going down on both sides, but either answer is acceptable at this point. Okay, so that's it. You survived the first lesson. Great job. Thanks for listening.